Thank you. And today is a special day. It's Canada Day. And I'm going to indulge and say a few words about that. Because on Canada Day, we also had something really special happened this year. Did you see the news about Joshua? Yeah. How about a big thanks? And it's very well deserved. Over the last 15 years or so, Josh has been one of the organizers of these summer schools with Joshua, with Jan, and many others have helped, some that are here, I see Max and so on. And many people who you know now are sort of big names in deep learning, whether it's Alex Grace, Ian Goodfellow, or you name it. They were sitting there where you are right now, learning about RBMs and all these other cool things that deep learning was about. And that would never have been possible if it hadn't been for all the hard work that Joshua put into this with his colleagues, with Jeff and so on. So this was a huge contribution, I think, to the world of science, and certainly to those wanting to understand intelligence. And most of those people are actually away in the United States, in Britain. So if you go to DeepMind, it's full of Canadians, and so is Google, and so on. We've given them our talent. We've given them our startups for cheap. We've given them our IP. And we don't care, because we like to give, because we're Canadian. And we believe in the greater good, and we look to the future. And it's paid out, because those organizations are coming back, those who have benefited from us are coming back and helping us here. And that, again, would not have been possible without initiatives like what you've seen Joshua doing here in Montreal. That's been really amazing for the Canadian economy, because it's all fine to sort of, for our institutions to be supporting research in other countries, but it's also important for us to have a sustainable basis here. And that's only the beginning, because we've seen a lot of stuff happening in Canada, but also we need to make sure that that's sustainable for the future. We need to make sure that the communities benefit from it, that we don't just go into a process of gentrification. And I know this is something that Joshua worries a lot about. And it's also going to be up to you, the next generation, to protect the same values that we've endorsed here. I remember many years ago, we had a dinner, and we were talking about AI and so on. And I was like, it's all hopeless because I have no faith in the humankind. I went through apartheid, I went through South American slums, I've seen the worst in people. But Joshua didn't buy that. He was like, there's good in people, and if you actually look at the global statistics, we're much better today than we've ever been. And we just need to keep doing good. And that's, honestly, over the last few years that I've known Joshua, he's always lived by that. It's not gone into the big millions and so on that he could have easily got from corporations and so on. But he lives a simple life, and he's passionate about what he does. And he's passionate about doing good things for other people, whether it's a plea for the environment or for science or for tolerance of religion, but also tolerance of atheism. And he's always been a champion for that. And I really thank you for that, because that voice was my inspiration. And lastly, Surya yesterday mentioned that it's not all about competitions and so on. Competitions are important, but I agree that it's about more than just competitions. Competitions are good to the extent that they help us advance our knowledge and the things that we can do to help people, and not just people, our planet in general. And nowadays this is obvious. 15 years ago, this wasn't obvious. 15 years ago, good luck getting a paper published on we're going to solve intelligence or AI or whatever it is that people claim they're going to do now. And it was very hard to sort of have those dreams and to talk freely about those dreams without being called a nutter. And I remember being in a CIFAR meeting, and this was a renewal. I think it's 2008, maybe 2005. And we were talking about what was going to be the next big project, and it had to be something big about AI that was going to capture the imagination of people and so on. And few people had opinions. We were not clear. I remember I thought I had a really clever idea. I mentioned in a meeting we should build self-driving cars, and that was obvious at the time already. So it wasn't such a great idea, but I thought, I quoted some figures. 1.2 million people in the world die because of car accidents. And it's atrocious that we're not stopping this from happening. So this would be a good thing to do, and also it allows us to extend what we can do with AI. And I still remember Jeff was standing there in the corner. And then he answered, he looks at me and says, "Why don't people take public transport?" And then he and Joshua proceeded to then say, no, it's not about this application or that application. And it's okay, applications are important. And of course, these things are useful because after all, that most of those people who die in car accidents are the pedestrians. So we should protect them. And AI has given us a lot of tools and will continue giving us a lot of cool tools for healthcare and so on. But then their plea was like, we need to study intelligence. That is one of the greatest questions, to actually understand what makes us what we are. And not just we as individuals, but we as communities. Intelligence is not something that arises just in a single individual. It's a communal thing. How does that process work? What are all the mysteries? How do we manage to sort of manipulate objects? These things are beyond what any of our machines are capable of doing. And at that time, they were very assertive. They said, we're not going to do any of these other things. We are going to go for this. We are going to go to understand, I think at the time, the brain. And so be it. That's what it became. We decided to understand the brain. And we wrote many papers on RBMs, and we stacked them, and we made them deeper, and they didn't work. And then we had many workshops like this one where we learned about GPUs. And some of the people in the audience, the Alex Krzyzewskis and so on, they learned about this. And then after 2012, I think more or less 2010, 12, with the successes in speech and ImageNet, the rest was history. Then the world realized the cool things that would have happened. Lots of cool stuff. And so one last time, let's congratulate Joshua for the Order of Canada. Thank you. Okay, so on to my topic for today. So I'm going to take a slightly different approach. We've seen some really cool takes on this. Thinking about problems as statistical estimation instead of optimization. That's really important in science that we got yesterday. Also about understanding the neuroscience behind deep learning and how deep learning can contribute to neuroscience and vice versa. We learned a lot about language, and I'm sure I wasn't here before, but I'm sure you learned a lot of cool stuff about generative models and so on. Today, I'm going to go on about a topic that is, for me, arises from these following questions. It arises from trying to understand what it is that machines can and cannot do yet, that we would think of as intelligent behavior or intelligent capacity. I'm always looking for what is missing. What is that thing that our machines can't do? So yes, it's about competitions and benchmarks, but it's not just about doing well at the competition, even though that's important. That improves our methods and algorithms and so on. But it's also about deciding what is the competition. What is the next challenge? How can we keep making the field go forward? And that's a very hard question, because you need to set a goal that is reachable. If we set too hard a goal, then this community will sort of fail at it. So that actually is one of the greatest challenges for us as researchers, and it's one of the greatest challenges for AIs, is deciding what we're going to learn next. So I'm going to start with a video of my daughter, Tala. She's 2 now. This is when she was 1. I wish I had sound. Let's see. Amazing. No machine that we've ever developed, and no machine that we have in sight that we think we will be able to develop over the next couple of years is capable of this. And I'm going to try to break this down into what Tala's doing here. She's able to reason about objects. She understands what objects are. She's able to reason about geometry, how to put things together. She obviously is standing. She knows how to stand. She knows how to move her hands. She knows all about contact forces and manipulation, friction, how to sense multimodal interaction with the world. And that wow when she succeeds. That intrinsic motivation, that's the same motivation that I think the reason why you guys are here. It's like that's getting knowledge. And we don't really understand this process really well yet. Why it is that we've evolved to seek knowledge. But this is what also drives us to do what we do. Another thing I wanted to show, it's where does it happen? Okay, so I'll play one last time. She tastes. And that's very interesting, that she tastes the blocks. And she's getting an understanding of what this thing is about. Who speaks, there's a few people here who speak Spanish. So there's the word, so when I was a kid, with saber, yo sé, and you confuse the past tense of those two verbs, of tasting and knowing. And this is a common thing. And that's true of other sort of Indo-European languages. Knowledge is to taste. So seeking to sense the world, to have a better understanding of the world, is something that is akin to searching for knowledge. Now, Tala was 1 when she did all this. She had just turned 1. And so one has to ask, how was she able to, in that 1 year, learn all of this stuff? And perhaps she didn't learn all of this stuff within a year, but perhaps when she was born, and she definitely was born with a brain, and that has a lot of structure, that allowed her to sort of get started. She was born with the ability to learn. Now, I'd like to argue that evolution endowed Tala with, and I'm thinking about evolution as a learning process that then gave Tala the ability to learn. So there is this process where learning happens at multiple time scales, and you learn the ability to learn at a different time scale. And this is not the only time scales. And by the way, I strongly recommend you read papers by Elizabeth Spelke if you're interested in this type of thing, where she looks at what are the sort of things that babies are born with in order to be able to best understand how they come to understand what an object is and so on. Let's look at a different time scale. So this is an experiment that Harlow did in 1949. And in this experiment, Harlow would show a monkey 2 objects, visually distinct, and behind those objects was a reward. So in this case, the monkey chooses the beer and gets a reward. At the next time step, the monkey chooses wine and it doesn't get reward. And then it chooses this other object again and it gets reward. So that's one episode. And then this gets repeated with two different objects. And the monkey chooses wisely first and gets a reward. It gets a reward, but then I guess it's evening time and the monkey chooses wrongly and doesn't get a reward. Another trial happens and the monkey decides to choose the beer, and it sort of makes sense. It chose the beer before, but it doesn't get a reward. And then it chooses the wine and it gets a reward. So what do you think? Will the monkey get a reward? How many people think the monkey will get a reward next? You're the beer drinkers. So the rest of, how many people actually think it won't get a reward? Okay, yeah, most of you are awake. So indeed it won't get a reward. And what monkeys actually learn, that you just learn with 3 examples, although monkeys usually go through many, many thousands of trials to learn this, is that they learn that the task is really about, you have to identify, once you pick an object, that same object will always give you a reward, regardless of the object. So the monkeys actually, through many trials, they learn this. They learn how to choose. They learn to solve these banded problems by doing multiple trials. So at the time scale of experiments, the monkeys have learned how to resolve a particular problem. When they encounter 2 objects, they try one. If they didn't get reward, from that on, they know they have to switch to the other one, and they'll get reward.
Can't we assume that the previous step was rewarded by mistake? Are we assuming always that the reward is correct? The person who's giving the reward always will not make any mistake and reward the action, not even with a very small difference?
So I haven't done this experiment myself, but I recommend you look at a paper by Jane Wang, one of my colleagues at DeepMind. And I'm pretty sure, so there they consider, and I'm going to come to this as well, sort of banded problems where there is uncertainty. And so there the rewards will be stochastic. But really what I'm trying to sort of say here is learning to learn happens at many scales. Okay. Okay, and if you're following what this crow is doing, you're seeing how it sort of learns to, in order to get the food in the tube, it learns to throw stones in the tube. And this one is really cool. It has to choose between getting 2 kinds of food. In one case, it's obvious that it can throw stones and get the stuff. In the other case, it's obvious that it can't. And so it changes task to do this other thing. So these Caledonian crows are capable of making tools. And I didn't say using tools, but making tools. They learned this by the age they're 1. And they learned this from they learned this from the other crows. So they learn it from their community. So they're capable. Whoops. Oh, how do I stop this there? I'll get rid of the distracting sound at least. They're capable of learning from their community how to do things, so they learn to imitate their elder crows. And just to tell you how remarkable this is, humans learn to make tools at a much later age. So the crows are able to do this. And this gets passed from generation to generation. So this is not, again, an ability that they will just learn once. But they actually really rely on this sort of different time scale of learning, which comes through their culture. And here is another problem that has become very popular in machine learning. It is the problem of few-shot or one-shot learning, where you're given a sample of a class, for example, like an omniglot digit, as Brendan Lake does. By the way, Brendan Lake and Josh Tenenbaum have a paper about human intelligence and contrasting human sort of animal intelligence with artificial intelligence. I strongly recommend you look at it. They pose some really good challenges for all of us there. And so one is this, that if we look at one character, we're able to easily go and draw other characters. Or we might see some object and we can sort of imagine this object in different sort of poses and slightly different shape. And one of the challenges they pose is, how can neural networks learn just from a few data? Because after all, when we try our neural networks, we have a lot of data. I mean, everyone keeps saying we need bigger data sets to train the models. But we also need to understand how we could use neural networks to learn from very few data, to be able to replicate this type of behavior. I would argue that learning to learn, and I will present in fact some examples by a few folks, by Adam Santoro and later by Hugo Larochelle, who actually show that if you have a model that is capable of learning how to use data at test time, then it learns how to, given a small data set, quickly learn to be able to provide you with an answer. Now, I've done some work in learning to learn over the last few years. I've been very excited about this topic because I think it sort of answers some of the big questions that we have. It's talking about development in animals. It's talking about how we can learn from few data. I think this is an important topic. It's one that we need to understand well. We do not understand it well yet. And I'm going to give you some examples, mostly biased to my own work. And they sort of give us some understanding of this and how we might be able to do it. But by far, I think this is still an open problem. And there aren't killer applications out there, like ConvNets and so on. But I think it's an important problem that we need to sort of work hard at until we either find that it's a complete wrong course of action, or until we use this theory to be able to understand better development and learning with few data. Now, the problem that I'm going to look at is, how can a neural network control another neural network? Or like in particular, how can a neural network be used to learn another neural network, or acting, say, as an optimizer? Or in fact, it could be an MCMC sampler and so on. It could be a network providing samples for another network. There's many variants of this work. Many researchers have worked on this. Max has worked on this. Joshua has a beautiful paper with his brother. Actually, not one paper. He has like 4 or 5 papers on this topic, learning to learn, where he was trying to learn unsupervised learning rules with other types of algorithms. I think those papers are papers of the time, early 90s. And should be revisited, because I think it's time to give it a modern treatment. So for people looking for topics, I strongly recommend you look for the Benju and Benju papers of 92 and 94 on this. The problem comes in many forms. There are folks that use one neural network to generate the parameters or the architecture for another network. In program induction, the parameters determine the behavior of the network. If the network is a recurrent network, essentially implementing programs. And so this is often known as programmable neural networks. It has a long history. It's in the paper of Rumelhart, McClellan, and Hinton. So one page only, but without experiments, but the idea is there. And many others have sort of thought about this problem. It's been reincarnated in recent years as well in the deep learning community, where people are sort of, again, trying to understand how one network can set the parameters of another network. And I think there was, someone already mentioned that here. Control, how can a network sort of control the behavior of other networks? So then we get into things like hierarchical reinforcement learning or gating. That again is a neural network choosing if either the activations or choosing the memory or choosing a bias of another network, and through that being able to control another network. And then of course there is this question of how do you learn one algorithm with another algorithm. And there's many variants, and I've called this learning to learn X by Y, where X and Y are two references, two variables, and you can plug in your favorite words here. So we've done SGD by SGD. You could learn unsupervised learning, as Joshua has done, with supervised techniques. And this actually is very interesting for neuroscientists, I think. So we saw these talks about neuroscience and how we're trying to figure out alternatives to backpropagation. I think this could say a lot about that, because you might be able to, instead of you hard coding what that unsupervised learning algorithm is or this alternative propagation, you might use backprop to learn that.
So actually that was the motivation of the paper with my brother in the early 90s, that we wanted to learn the synaptic learning rule because we didn't know, what the right answer was. So we would parameterize a synaptic learning rule with a small neural net that only looks at what's happening around that neuron, and then we would optimize that through backprop through time to perform some tasks. So it was exactly trying to deal with the biological question of what is a good synaptic learning rule that overall gives rise to good behavior. And we also had the idea that the outer loop could be either backprop, but could also be evolutionary algorithms, and we tried genetic algorithms and stuff like that. Just like evolution figured it out.
Indeed. Yeah, I recommend it. And in fact, when I looked at that, you also looked at simulated annealing and so on. You basically threw all your Y was everything you had available to you at the time, and your X was the sort of alternatives to Hebbian learning. I think we need to sort of revisit that nonetheless with modern tools, because our Y has expanded and our X, and we know
the computational power here makes a big difference.
Indeed. I'll come to that. And you could apply this also to inference as well. And I think there's a few papers that have already looked at this. So how do you learn sampling? How do you learn, for example, Langevin Monte Carlo algorithms with another algorithm? So what we did was simple in a way. We just basically noticed that when you do have a learning rule, typically you have this update where you have a network of parameters, say theta, and you take a step in one way or the other in the direction of the gradient. And then what people do is they spend a lot of time trying to come up with a transformation of these gradients, whether it's RMS prop or Adam, until they get better results on MNIST. And eventually they test on bigger data sets. Or others in the community do, and through the community we come up with better algorithms. But the process of designing such algorithms is sort of, it's basically feature engineering. Just like with DeepMind's, we like to say, let's stop doing the feature engineering and learn the features. Engineering optimizers is still feature engineering. And so perhaps we could aim to actually learn these optimizers automatically. So that's a dream. And that was work that was done at DeepMind with my colleagues, Marcin, who is now at OpenAI, Misha Daniel, who still works, the rest are all at DeepMind, Misha Daniel, Sergio, Matt Hoffman, David Pfau, Tom Scholl, and Brandon Schillingford. In machines, so we go to the world of TensorFlow. And the way this was engineered, and not easily, because for any of you who know TensorFlow, if you're going to modify the learning algorithms, this is a lot of hard work. And Matt Hoffman and Sergio actually spent a long amount of time working on the software. And they actually put the software online. It's one of the most downloaded pieces of code, I think. And I really recommend it, because they're really good software engineers and they put a lot of effort into it. And so what their modules do is essentially you have two networks, an optimizer and what we called this new word that we coined in English, the optimizee, the thing that gets optimized by the optimizer. They're both networks. The optimizee could be, say, a convnet. So F implements a convnet, and it gets a loss, say supervised loss. And then you have this other network, which is, say, a recurrent network that has some internal state, and it generates the gradients for this other thing. So it provides this network with parameters theta with the update step. And then this network itself is a dynamical process that's unrolling over time. So the new gradients are being generated by some network. And this network might look at some information from this other network, like gradients and so on. But instead of looking at gradients, you should also consider, and this I'll leave as a homework exercise, to take everything that you saw yesterday as alternatives to gradients and learning rules and plug them in here and see if you can get this to work. So that's more or less the idea of the approach, is use a neural network to adjust the parameters of another network, and then you just generate one big network. So the optimizer and the thing that you're optimizing is a single network. There is no longer the algorithm and the model. It's all a single network. Uh-oh. Battery? Battery's dying, I think.
I have some batteries here.
Not this one, the other one.
Oh, it's that one.
Yeah, battery is there. Should work.
Test? Okay. All right, so yeah, deep learning consumes a lot of power. We need to make it more sustainable. Oh, where was I? So yeah, so the whole thing is just a single network, just like the brain. It's a single network affected by environmental influences, and it's a dynamical process, sort of moving, it has dynamics. And in fact, the brains with other brains and working together, also a dynamic process. And so just in the same way that we look at the universe as this process on space and time, I think that's a good way to be thinking about minds and brains. The particular instance that we chose here was a coordinate-wise optimizer, where you sort of take a parameter, you pass it through the convnet, the thing that the optimizee, you return, you get the gradient, you plug into an LSTM, and it gives the update. The update gets added to the previous value of the parameter, and then you go back and you generate a new parameter. And the reason why we chose to update just one parameter at a time in this particular instance was because we wanted to be able to learn to transfer to models of different sizes and so on, to be able to transfer the optimizer. So one thing that we were interested was in, you learn this joint network together, and then you sort of cut the optimizer and move the optimizer to optimize other functions. And we wanted to test how far could we push this. And so the first thing we tried was MNIST, like everyone else. And we trained with a small network with 20 units in the hidden layer. And we observed that the optimizer that we were learning was doing better than some very respectable competitors like Adam, RMS Prop, SGD, and Nesterov's adaptive gradient. And then we tried it on a network with more units, with 40 units, and it still was working. So this was exciting. And we were doing this with 100 optimization steps. So here we need to enroll the LSTM for 100 steps when we do training. And then we went to 200 steps, because then there's this question, if we were to enroll it further, what would happen? And so this seemed to be working still. 2 layers, boom, here we were so happy. we're like, that's it. We're going on for the next big award. And then this happens. We went too far outside the model class for which we had trained. We're doing these transfer experiments, and eventually we figured out how to break it. Also good for experimental methodology. Don't just go and publish the results at work. Try to find the ones. Try to always see where you break it.
Just to clarify, you trained it with 10 units or something? Like
Yeah, thank you for the question. Yes, I forgot. So the question was, what did I train it with? 10 H units. And so it didn't know how to deal with ReLU units. The paper has more experiments than we go and study how you do ReLU to tanh and so on. But I'm going to skip that because I think we have now different ways of doing this that work better. And then we did the same experiment for other data sets. So we did and tried this on CIFAR. And in particular, we were looking at transfer where we're still using the same network, but we sort of learn with 5 labels. And then we go at test time, we try to learn 5 different labels. Or we learn with 2 and then try to learn with 8. And again, we were doing pretty well in comparison to these other competitors. And then we tried neural art. So most of you probably know this neural art work where you sort of have a painting and you have a photo, and then the idea is you want your photo to look like the painting. And so this involves, who are the authors of that paper, the neural art paper? It's Matthias? Yeah, sorry, I should have put a citation to their work. And so we're using exactly what they do, but that involves doing an optimization process, basically, as part of. I won't have time to go into their method, but you do need to you're required to do some optimization to come up with this image. And here we were able to do that optimization with these methods, and we were able to give it new content, so new images, and be able to sort of generate this for a particular style and a particular image size. And even more exciting, we were able to try completely different styles and content and sizes of images, and it still worked. So we had learned an optimizer that could transfer for this particular application. And it was doing better than the first order methods that we tried. But there were some challenges left. And we realized this by doing more experiments. And so we didn't stop there with that. So we got our paper and so on, but we continued trying to push the work. And we found there were some challenges in trying to, and in particular, we wanted to scale this. You know, this is only, it's all cute to do CIFAR and data sets and so on, but we want to do like the big things. We want to do ImageNet. We want to train, you know, at the time we were ambitious, we wanted to train the whole of Google products with this stuff. And, you know, and you have to have that sort of ambition because eventually you sort of hit you have to push as much further as possible, and in particular with scaling. We do realize that still, I think this is one of the biggest challenges is how we scale our networks. And what we found was that because we're using these LSTM optimizers, and even though they share parameters while updating a single parameter of the optimizee, they have a lot of activations. And because they have a lot of activations, you need storage in the GPU for those activations. So now all of a sudden you have a trade-off. If you're training a ResNet model, because you're running out of memory in the GPU, you need to make the ResNet model in order to make room for the optimizer, which is also a neural network. And so this is a difficult trade-off to deal with in practice because we want the optimizee to be as big as possible, at least in supervised learning. In control is a different story, and I'll come to that next week. And the other issue is all the optimizing horizons that I've described so far, they're fairly small because you don't need to optimize for many steps to do well on MNIST and so on. But if you go to ImageNet, you do need to optimize for many steps. And so you need to unroll these optimizers for many steps. The generalization has to happen not just to 200 steps, but it has to happen to thousands of steps. And of course, there were the RELUs still. And there's another challenge with this, is these experiments are really expensive. Okay, we're learning to learn. And the first learning, as I argued before, that's evolution. Evolution has endowed Tala to learn to put blocks together better than any existing machine. But that process of evolution was very expensive. And I'm not sure we can actually sidestep this by going this approach, by going this way. And I have no answers for this particular question yet, but Joshua seems to.
Well, I think evolution gives us a very strong clue that we should look for an outer loop learning which is parallelizable.
Yes.
Because
so that's
a million processors much more easily than one that is a million times faster.
yeah. What I would say is not only that, but we need to understand evolution properly. So for a long time, there's these papers on evolution. There's good work, very good work out there in evolution. But there's also many papers where people just run things in parallel and they call it evolution. Or they do, you know, and like I feel like that meta optimizer, we still don't understand it really well. And it probably would help to understand it better, to at least to be able to advance this kind of research.
So why is it important to get this to work on ReLUs? Because my understanding is that ReLUs are important for solving this gradient vanishing issue, but if you're injecting gradients, I mean, why then do you need to get this to work on ReLUs?
True. I mean, there might be reasons. So the question is why focus on ReLUs, and in particular, there's reasons for why maybe ReLUs are only used because the optimization is hard and so on. I still think some people would use ReLUs because, you know, they have some biological considerations, for example, as to why ReLUs sort of might make sense. But also, I highlighted ReLUs here. But what I really mean is it has to work for everything, not just ReLUs. But ReLUs is the one thing where I've shown you that it fails, but it could have failed at many other things. And so I'd like to design optimizers that are capable of transferring and solving many things. And so we're going to scaling and generalizing. And I'll go quickly over this. And this was mostly the work of researchers in Mountain View. In particular, Olga, she worked so hard on this and she put a lot of effort. Together with an intern at Google Brain, Niru, we've already seen a citation to him yesterday, one of your students, I think, as well as Jasha Scholl-Dechstein, who led this project. And so we teamed up with DeepMind, teamed up with Brain to be able to sort of address this issue of scalability. And there were many things we tried in doing this, and the work will be presented at DeepMind for any of you who want to see more about it. So there were several things we decided to do differently. So first, we decided that instead of just this idea of training on one data set and still testing on that data set, Joshua had this idea of let's train on lots of different data sets. Let's train on simple black box optimization functions and random functions and generate sort of random data and fit logistic function to it and so on. So a huge range of training sets. They were small. He also randomized the length of the training and so on. So the idea is let's try to sort of have a lot of variation in this data set. So hopefully the optimizer learns to deal with all this variation. He also introduced a hierarchical LSTM that it requires less parameters and less activation, so it's a bit more efficient. And also made a design choice of let's not just like completely obviate all the insights that we have gained from the theory of optimization, but let's use some of these ideas. I mean, we know that normalization and so on helps, so we shouldn't ignore it. Let's just feed in some of this stuff in. And then also, by training with different lengths, as I mentioned earlier. And the result of doing this was the following. So let's look at the ReLU example here again. And let's also look at optimization over many steps. And now we're starting to look at 100,000 steps. And once again, if we actually look at this inset here, so we magnify, we see that the new sort of approach is still able to do comparable to Adam, and it's able to actually do better than RMS-prop in this case. The old approach that I've been showing you before with ReLU completely diverges, as we saw earlier. But when we train this with convnets on MNIST, perceptrons on MNIST, the learned optimizer still does a very good job. And eventually sort of asymptotes, but it even has a faster rate of convergence at the beginning than optimizers that we use regularly.
Do you use truncated backprop? Because it's too long, right?
Yes. Yeah, we do. I
didn't explain truncated backprop, so maybe you could.
Go and explain truncated backprop now. I'm not going to have time. I do have some lectures online. So Google Deep Learning, Nando de Freitas, Oxford, truncated backprop. So we are enrolling the LSTM. Oh, I'm not going to have time to cover backpropagation through time and truncating it. But basically, as you go further back to compute the gradients, often you have to stop from going too many steps. And that's pretty much it. And there was one more thing I wanted to say about this picture. I highlight again. It's doing well on these convnets. This was not trained in neural networks. These optimizers were trained on random functions, logistic functions, functions from the optimization literature. So there's this complete transfer to deep learning from other classes of problems. And then Olga struggled for a long time, but she managed to eventually get results for ResNets and inception models. And it's still, this is kind of where we are right now. So the learned optimizers, they still don't do as well as the competitors, but it's quite remarkable that we are scaling. We're able to run these optimizers on the sort of state-of-the-art models and not necessarily the worst. So we have made progress. And I think we're still short of a few ideas that hopefully will eventually take us to actually beat the other optimizers. It might also be very hard to beat the other optimizers, because the other optimizers are things that we've been working on for years and using very smart brains at it. But this certainly, I think, shows that learning to learn can scale. It can happen.
Quick question. Wondering, can you just say something about the hyperparameter? Just wondering if there's something other than just the initial learning rate or things like an atom with various dimensions.
Yeah, good question. Thank you. Hyperparameters. So with the training with LSTMs and so on, initially during training, you do come up with the usual hyperparameters for training these methods. And in fact, at training time, we use Adam. So we're sort of learning to learn by Adam. So there's actually 3 levels of learning, I guess. But once we've trained the optimizer and we remove it from the big neural network and we're using this optimizer neural network, that optimizer neural network has no hyperparameters. So unlike the other techniques which you have to tune to the data and you have to figure out the hyperparameters, this one has no hyperparameters at all. So this issue that we were talking about of doing hyperparameter sweeps and so on, that's gone. Please.
Yeah, I was wondering, another way to get a robust optimizer, would you need to do few-shot learning to learn? To start on a certain data set and then try to sort of adapt the optimizer to the new one using just a few samples?
You're definitely right, and I'll have a slide on that. And instead of repeating, I'm going to bring that slide. So it's about being able to do few shot optimization by thinking of it as in the process of learning to learn. Go ahead, David.
Any dramatic failures of this learned optimizer?
I've shown you some.
Like this?
Well, you saw what happened with the rellos before. I'm sure this optimizer, I'm sure if we push it really hard, we eventually will get failures. There's no doubt of that. So, and that I think is true of most of even the optimizers that we hand engineer. You can then construct objective functions that sort of break, I don't know, continuity and so on, and eventually you can sort of get them to break. For the things that Olga and Neera and Josh and Matt and Sergey have been testing, they seem to be working reasonably well. And so the problems that we've tried are the same problems that everyone is trying, and in particular this type of thing. So one thing I haven't talked about is RL. So actually that could be a good example, where if you deal with a lot of variance, if there's a lot of variance, we haven't quite addressed that problem. That would be worth studying.
What are the assumptions on the loss function for this optimizer to work? Like, can it try to optimize the 0-1 loss, for example, and then optimize very discontinuous, nasty functions, or is it just learning on the subset of functions that you are training, like the continuous nice surrogate loss functions that we use in that we currently use?
Yeah, so it's we sort of training on a bunch of types of loss functions, and then we're testing it on the type of loss functions that arise when machine learning, like in particular sort of the type of losses that we use in deep learning. It's possible that you could come up with other losses with discontinuities or with a lot of noise where this could break down. But then the solution would be you would have to train in those losses as well.
So my major question, I'm curious, do we, because we use surrogate loss functions because of the optimization failure, because of the shortcomings of our optimization algorithms, right? Because they can't handle these. Can we go back and not use surrogate loss functions and use like the 0-1 loss and train this to handle the 0-1 loss, for example?
Yes, you could do that.
Okay.
Homework exercise. I'm going to give you one other example of this, and there's been a lot of mention of hyperparameter optimization. So, and I'm assuming that Michael Osborne talked about GPs and Bayesian optimization.
Yes.
Yeah. Okay. So you're kind of seeing what it's like. You sort of have basically it goes like this. You have only 2 data points, and there might be some true function which you don't know, which is this dashed function here. And then you have to decide where do you pick the next point to learn the function. So it's a problem of active learning where you're trying to learn where is the maximum of this function. You're looking for this maximum here, or the argmax here. And then what you do is you do you trade off exploitation and exploration. So ideally you would like to pick something that's near this point next because this point had a higher value. But you also need to take into account that there is, your model has uncertainty, and as a consequence of your model having uncertainty, there is also, away from the data, you always observe this. There's uncertainty there. And to make decisions, you have to take into account this uncertainty. In this case, this is almost deterministic, so where you sample, you actually get a perfect observation of the function, but you might also have noise in the observations. So that's the model uncertainty that we usually model in deep learning. And this would be the sort of Bayesian uncertainty, the uncertainty about your model or your parameters. And you need to trade off. So you want to look in areas where you haven't looked, but you also sort of need to look in areas where you know you've done well. And Bayesian optimization sort of has many ways of trading this off. So you might say pick a next. So you might have some function which we call the acquisition function, which we engineer to trade off between the sort of exploitation and exploration. This function tells you where to look next. Then we conduct an optimization of this function to pick the next point. And I'm assuming Michael would have told you about probability of improvement, expected improvement, entropy search, Thompson sampling, the million ways in which you can do this. And so on until you get to the optimal. And this is a very useful technique for tuning the hyperparameters of neural networks. It also has some challenges of how to get this done in practice. We were looking at this and we're like, well, can we just replace that GP process and the process of having to optimize a surrogate just by using a recurrent net? Let the recurrent net learn to pick the next point. Let the recurrent net learn to do active learning, learn to do optimization. So we decided to do the following. We sampled, and here we knew that GPs sort of work well. So let's construct a very large class with different kernels of GPs, and let's just sample many functions from the GP. So this is sort of related to the previous question. And for those functions that you sample, we can run the GP, we can run sort of the Bayesian optimization, and we can also train an RNN because you know the values x and the function values, and so you can have an RNN that has some internal state, looks at the previous values, the previous input and the reward that you got, and decides what the next x should be. And then you evaluate the function, get a loss. And after several steps, you aggregate all these losses, and you backpropagate, and you learn basically the RNN that is choosing the next point. And so this work was done by Yutian Chen, who was a PhD of Max, Matt Hoffman, Sergio Gomez, Misha Daniel, the same people that were involved in the other project, and Tim Lillicrap, Matt Botvinnik, who are my colleagues at DeepMind who work mostly in neuroscience. And Yutian also came up with this idea of doing this in parallel, because when you optimize neural networks, you don't want to wait too long for the answer to come back before you try your other model, especially at Google, where you launch many of these jobs in parallel. You really can evaluate the function in many machines. And so it would be nice to be able to take the previous observations, but we also introduce a variable that indicates whether there's still resources available, so it's a binary variable, or whether there are no resources available. And with this, we're able to actually do this in parallel. So as soon as a machine stops and gives us an evaluation, we're able to incorporate it into the learning process, and we sort of reuse that machine. And one last thing we did is, instead of using LSTMs, in this project we found the differential neural computers, or what used to be called the neural Turing machines, a variant of the neural Turing machines, to work better. And so there's many ways in which you can do this, and all of these different ways will sort of be using these different acquisition functions. If we use them to learn as surrogates, we'll be doing sort of different trade-offs between exploration and exploitation. Well, the one that we found that worked the best was to just use this thing, observation improvement, which is a sort of a sample version of the expected improvement. What
are the axes here?
So what I'm showing is this is a function that we're optimizing, and this is just the parameters that the optimizer is training. So you're sort of seeing a run of what is training many things and how it's sort of converging to the optimal. Thanks. So we first tested this on GP functions, samples from GP. And of course, the methods that were designed with GPs, like in particular things like spearmint, which learns the hyperparameters or integrates out hyperparameters with HMs, with slice sampling. One spearmint with fixed hyperparameters. We also looked at things like TPE, SMAC, and so on. And we found that we sort of were doing comparable to those techniques in horizons of length length 100. For all these experiments, we assume that the setup is you're going to have 100 steps to reach your decision. And so this is very common, like in web applications. You can show customers ads 100 steps, and after that, it becomes too costly. So you have a finite horizon at which you can try things to decide what is best to deliver, or the experiment. Or more interestingly, if you're doing clinical trials, you can just do so many trials, either because of whatever resources you might have, economic or humanitarian, before you can actually choose the drug that you're going to use. And we then moved on to try this for the typical global optimization functions that people use. And then we're starting to see that these versions of the DNC in green and red are doing better for the particular horizon which we train than the tools that folks use out there. And these are tools that are very popular. They're well-developed packages. So this is, again, proof that learning to learn can do a good job. And of course, the optimizers here, after you learn them, they don't have any hyperparameters. So anyone can use them. And they're much faster. RNNs are much faster than you having to do an optimization, like when you maximize expected improvement.
So can you say something about the transfer between particular families of optimization functions and others, or was trained in the same family? Or is there
Yeah, so that's a good question. So what we did is we trained in just many functions of GPs and so on, because it sort of made sense for us. And then really the rest of these slides, what they show is the transfer to different other problems. So now this is showing that it can transfer to these benchmarks in optimization, you know, these simple functions in 2D, or these functions in 6D. And these are sort of optimization problems that have many minima and so on. They're sort of constructed adversarially by folks who work in this area. And it's still able to transfer. This is the same RNN. We're deploying the same RNN for different problems. We learned it once, then we use it for all this. It worked here. We tried it in a control problem. It worked well. We tried it on optimizing a neural machine learning architectures. This is here we follow the same examples as in the Spearmint paper. And we're again doing better than even Spearmint. Some of the tasks like, of course we have to do better because we're coming after them. But nonetheless, it's showing that you can learn an RNN that is capable of solving these optimization problems, tune the online LDA, tune SVMs, tune logistic regression, and in fact even can be used to tune ResNet and so on. So you could use a recurrent net to do the meta tuning of your network. Here you can see that the Spearmint still does a bit better job in trying to optimize a ResNet. And of course, as I said in the beginning, we're still not yet there. But we are very close, and we need to keep working on this. And we're short of some ideas, and I hope that it's going to be you that will go and figure out some of these ideas if we don't get to them.
In the initial learning, you used Adam to learn the first RNN.
Mm-hmm.
Have you ever tried to take your learned optimizer and go back and learn the optimizer in the first place?
That's a very good question. So instead of using Adam to learn the RNN, could I learn a network that learns that network that learns another network that learns another network? That is to be done. And that's my last slide. We did try here, because the DNC itself had some hyperparameters. So we did try to use this learned optimizer to learn the hyperparameters of a DNC that would then be used as an optimizer. I know Yuchen tried that. I don't remember how well it did. But actually, I think there is something there. This process of recursion, I think, is not just a joke, and there might be.
I think I've seen a paper.
On learning to learn with multiple recursion.
We made like a side function tool. The thing you might be able to do is make it small.
Yeah. So I think there's good computational reasons for this. So there was a really good paper at iClear on using recursion, but that was for the neural programmer interpreters. Where instead of training it with, say, to do for loops, it do recursion. And as a consequence, you end up with much shorter programs. And then you're able to then show things that are remarkable, that a neural network trained to learn to sort sequences of, say, length 20, can actually sort sequences of arbitrary length. It can generalize indefinitely. So in a symbolic sense, it is capable of doing that sort of thing. And that's only possible through recursion. Moreover, the authors in that paper they actually prove that it will generalize for a sequence, because the problems are small enough, you can actually do verification. So yeah, there is something there that I think is very important. Now let's look at some other, what I think are some other interesting works in this area. One of them is there's this paper in Archive by Jane Wang that I already alluded to on learning reinforcement learning. She actually uses reinforcement learning to learn things like bandits, or in fact learn to do the Harlow task, and learning to navigate. Raya Hatzel and a few of my other colleagues at DeepMind also have a paper where they sort of do something on navigation that is sort of learning to learn. And that's very similar to a paper by Berkeley OpenAI called RL squared, RL to the power 2. They're also trying to do this sort of thing, learning to learn. One interesting paper that sort of was very popular in social media and so on was this paper of Barrettsoff and Kwok-Lee, where what they do is they still have an RNN controller, as they call it, generating the structure for another network. And so what they do, for example, for ConvNets is they have an RNN that chooses the number of filters, the filter heights, the filter width, strides, and so on, and then moves on to do the next layer. And because it's choosing these discrete variables, so this is like a grammar for generating the networks. And so they train this with reinforce. This LSTM will choose basically the architecture of the other neural network. And then you run the other neural network on data and you can see how it does, and that's your reward. And then you repeat this with reinforce. This is extremely expensive. I've heard some stories about how much energy this experiment consumed, and it's borderline the sort of thing you shouldn't do. But it's really sort of challenging. It's challenging how we might be able to, in fact, have a network that completely learns a new network. Okay, so this is all of you should be worried about this, because this could put us all out of a job. The intention is to have networks that invent new networks. We're not yet there, but I think it's a very interesting exploration. Still, what it's capable of doing, it's nothing but just sort of, it's not yet capable of the kind of invention that we humans are capable of. Another very cool work, and this is related to the few-shot learning question that you asked, is this work by Sachin Ravi and Hugo Larochelle, where they have a meta-learner again, and they have some optimized, which is a ConvNet in their case, which takes some data, and it might take, so the data will be, say, for example, 5 images with labels, and then there's a test, and you want to, and just from 2 images, so when you use a test time, you see 2 images, and you want to generate a label. So the training set is only 5 images. So you want to be able to train, so you want to have many examples of this type of problem, where you look at 5 images and the labels, and then given 2 images at the test set, you need to generate the label. And so the way they do this is they feed, and here the index is time. So this is capital T iterations. X and Y is basically a thing that looks like this, 5 images with 5 labels. And you feed them in, and with a setting of the parameters, you get the gradient out, and then this LSTM chooses the next parameters. You again go forward, backward on this, get a gradient, etc. And eventually you get a test, and then this optimized Z, which he calls M, which looks at the input image X, looks at the parameters that this guy's provided from running the LSTM on this, and then it predicts the label for these guys. And at test time, you minimize the loss so that it gets the right labels. At inference time, you see 5 images, and you're able to, from those 5 images, predict what the labels are. I think this is one of the coolest works that I've seen in machine learning for a while. Because it really, you learn how to, at test time, be able to use just a few data and capitalize on that data to provide an answer. Of course, there are other ways of doing this, and there's, I think, other ways that are even more effective than doing this. But it's interesting to see that you can actually do this in the same framework as what could be used for many other things, as I've shown in the setup for learning to learn. This one shot or few shot thing is becoming very popular, and it's important. So there was this very cool paper also from Yan Duan and colleagues at Berkeley and OpenAI, where they take a policy network, pi, that produces actions A, but they condition not just on the current observation of, say, a set of blocks on a table, but they also condition on a demonstration. And so they train models of this form. And what these models then learn to do is at test time, they can condition on a new data set. So if you see a new demonstration, then you know how to, you learn how to have a policy that regardless of what demonstration you're going to see at test time, and you don't know what data someone's going to give you, you don't know what someone's going to try to teach you at test time, but you learn how to react to that. So you prepare yourself for the lesson. And I think that's a very important direction, because it's sort of, we start designing models that don't have this sort of fixed architecture, everything is stored in the hyperparameters, but you accept that at test time there's going to be some data, and you're going to have to know what to do with that data. There's a video of how they do this. I'm going to just skip it and just mention something very quickly. And I want to go back in the last 3 minutes before I open the floor for questions, and go back to my daughter Tala and what she was doing. She was experimenting. She was working as a scientist, trying to figure out how to do things. She had these internal rewards. She was able to put Lego blocks together, and she was able to take them apart. And again, I emphasize, no machine that we have today, or no machine that we have in sight to develop over the next 2 years, is capable of this. There's all sorts of outstanding problems that you can sort of think about when you look at that. But Tal is not alone. This desire for knowledge is much deeper. It's the desire to sense as well. It's what sort of led to us having eyes and ears and constructing machines that enable us to do more sensing, like telescopes and radio telescopes and microscopes and so on. Computers, for that matter, and why we're building AI. Trees have this. Trees have opsins, which are the molecules that seek light, and they use it so that they can find light and grow beautiful leaves and provide oxygen for us. We have the same things. We have opsins, different variants of these molecules, and this is how we kind of learn to see. And they gave us an advantage through evolution, through a process that, again, I emphasize we don't understand well, but brought us where we are now. And this quest for knowledge is one of the most important ones, and that we need to understand to get at what intelligence really is about. I'd also like to contrast what we do in deep learning, what I learned when I was an undergrad. In physics, we try to come up with models, in physics and many in the sciences, we try to come up with models that sort of represent the world. And in statistics too, that's kind of what we do, and we accept that all models are wrong, some are better than others, and some do good predictions in a setup, but they might not do good predictions in a different setup. We try to come up with explanations, mathematics, and Surya gave us a good example of that yesterday. And then we also try to make predictions But we don't just predict that a model, it's not just about the model predicting this, but it's the model predicts something, and it has to also tell you how you could verify my prediction. What's the experiment that you can conduct to verify that indeed the Earth is not the center of the universe? These are questions that took us 100,000 years or so to figure out. And importantly, you want to be able to verify your predictions. So you want to get to the heart of explanation. It's not about having an image and generating a descriptive caption that says what's in the image. It's about being able to explain. It's being able to sort of get to the causal mechanisms that require understanding. It's not just assigning a label to a set of pixels. It's about being able to reason about what's happening there in that scene and so on. And it's only through that we're going to get rid of these things like adversarial examples and so on. So this kind of led us to start thinking a lot about how do we learn to experiment. And we've then taken a few humble steps in that direction, but I think a lot more needs to be done in this area. And I think this, in particular, these 3 lines, which I took from my undergrad physics book, are worth thinking about more than ever. We saw already a creature experimenting before, the crow, that interacts with the environment. It eventually learns to choose something, and then it gets a reward, it gets the food or not. And so Misha Daniil, Pulkit, who is an intern with us at DeepMind, and he's at Berkeley, Tejas, Tom Aris, Peter Batali, and I decided to try to understand how you could interact with your environment, to learn about your environment. And we decided to make it interesting. So we decided that we want to address problems where you really need to understand the physics of the universe. The agent is not completely disembodied from the world, but we're assuming that the agent is in an environment, and this environment is what determines its intelligence to a large extent. And by the environment, I mean other agents as well. And so, in particular, we were looking at a setup where, imagine that the agent cannot sense. Let's strip the senses. But let's allow it still interact with the environment. So if I put a thermos here, I don't have one, and I ask you, does it have coffee in it or not, you will not be able to answer that question. The only way you can answer that question is by actually standing up, walking here, and picking it up. And then you can tell, well, if it's heavy, you probably say it has coffee, or you might have to open it and taste it and check that it's not tea. So for a lot of perception, we actually need to act on the world. We need to conduct experiments. And so what one of our interns, Ed Choi, did was he had a setup where there were piñatas of different weight. And this is in Mujoko, so this is a physics engine that has gravity and a ground flow, friction, etc. And then this little guy moves around, and it has a hammer. And it has to learn to apply the right torques and how to move and how to touch these things. And then it has to stop, just like the crow, and it has to tell you which one is the heaviest piñata. So here the heaviest is the first one. But this is an agent that hasn't learned, so it's not very good. If you train this with reinforcement learning, then this agent moves around. In this case, the yellow one is the heaviest. And just by touching it, already realizes that, wait, this one is the heaviest one. And it tells you that that's the heaviest. Now, how does it know this? It was trained with many instances. So this is again like the Harlow task. It was trained on many instances where there was one thing that was always somewhat heavier than the others. We did many other control experiments, it's all in the paper. But in this case, one of them is much heavier. So it can't see, so it's trying things. And then when it gets to one that is much heavier than the 2 other things that it has tried, it already knows, because one thing is always much heavier than the others, it already knows it must be this. So it doesn't need to try the other things. Where this is interesting as well is because we're training this with reinforcement learning. But for those of you who know about bandits, what this guy is doing is solving a bandit problem. It's a known to her, or him, or whatever gender this guy is, it's unknown to this creature what a bandit problem is. All it knows, it has to interact with an environment and it has to get reward, and it tries a few things, and there's in fact this weird mapping. The other thing is, in this case, we didn't have pixels, but you could also try to now endow the agent with pixels, and then sort of it learns with one modality, but as a consequence of learning to interact with the world with one modality, touch and so on, it will then learn to understand weight through pixels. Like, I can now look at that and I can predict its weight, and all of these objects, I know what their weight is from pixels. There's these weird objects that I've never picked up, but I can predict their weight. I can decide whether I can lift it or not. And I can even project it, maybe I can lift it. So I sort of have an idea about it, but I didn't learn this from pixels. I learned this because I interacted with the world. Actually, there's some other experiments, but I would like to stop and take some questions.